Now, this is a conference in the memory of Vladimir Voevodsky, and his influence was felt on many people and in many areas, and started actually quite early, going back to his early days. For me, I realize it is hard for me to speak about influence on other people. I can speak only about myself, and on me the influence was profound and long-lasting till this day. So, and some of his ideas that made their way into mainstream, they even now seem so obvious, they not recognized as such. So maybe I'll start just by saying that one of ideas very close to his heart was the idea of higher dimensional algebra. Something where formulas would have the shape of cell decompositions, polyhedral decompositions, pasting diagrams, and things like that. So in more categorical language, this is incarnated by the hierarchy of levels of objects, which appeared here. Appeared in this conference, even in type theory. So in the very simplest level, it is hierarchy between numbers. On the one of the lowest level would be numbers, maybe that's not the lowest one. So the higher level would be, say, vector spaces or objects of categories. And higher would be categories. And sometimes it's interesting to look at triangulated categories, but not always. And a simple example of going up this ladder is what was already discussed here, is a passing from Euler characteristic to cohomology or homology, or to categories of motives, or in symplectic geometry Fukaya categories, which also can be seen as some categorification of homology. So what I want to talk about is an attempt to set up something on this level, a generalization of a concept of sheaf, or rather of perverse sheaf. So let me explain this briefly. So perverse sheaves are, again, objects of some almost motivic nature, but I will consider them from elementary point of view. So we have the category associated to a stratified space. Suppose this is a complex manifold, and this is a complex stratification. So then this is an abelian category with duality. Abelian with duality. So the category is abelian inside triangulated category of constructible complexes. So and here complexes or sheaves are of vector spaces, say, of and we would like to ask if it's possible to develop a theory where vector spaces would be replaced by triangulated categories, or some version of this concept. Well, if you're talking about sheaves of categories, it is it's a sort of categorical analog of sheaves. It is a known concept and can be, by now, can be pursued at any level of depth, even at the triangulated level, when we consider triangulated enhancements, infinity categories, stacks, and so on. So let me write sheaves of categories. That's the concept of stacks, possibly with infinite descent, if needed, with respect to higher structure. But when we, in the definition of perverse sheaves, a priori they are complexes. And talking about complexes of categories seems a little bit, maybe possible, but a little bit like overreach at this stage. So at least it's not immediately clear that we should simply set up like a powerful truck and generalize everything to complexes. So let me put a little of question mark here. So it's not completely clear how to classify sheaves or complexes of categories. That's something to think about, but I don't want to run ahead of what's natural. However, let's consider a particular example. Consider the simplest category of perverse sheaves on a, say, complex line with singularity at one point. So this category has a classical description as a category of diagrams formed by two vector spaces, phi and psi, two maps A and B. So phi is known as the space of vanishing cycles, and psi is known as space of nearby cycles. And the condition is that 1 minus AB and 1 minus BA, such endomorphisms of phi and psi are invertible. They correspond to monodromy on the spaces of vanishing cycles. Now, this concept, in fact, has a transparent categorical analog which has been known for some time in category theory. This categorifies two. Oh, I should say that my talk is based on joint work with Tobias Dickerhoff, William Schachtman, and Jan Soebelman. So this concept has a categorical analog, and this analog is known as the concept as spherical functors. This has been defined by Rina Anno and Timothy Logvinenko. And there's the following structure. Suppose we have two triangulated categories, B and C, but not in this general theory. Most of the time, it's important to consider triangulated categories with enhancement, either with a DG structure or with enhanced in the sense of stable infinity categories of Lurie. So let's call triangulated with possibly DG, but not necessarily enhancement. It means that maps space of homomorphism in this category is really cohomology of certain complex, which is part of the data. And suppose we have a functor, DG, again, functor F. And suppose this functor has an adjoint. Let I write adjoint. As I do, we can write transpose of a matrix. Say right adjoint. So, of course, in this question, in this situation, the question is what do we mean by adjoint? So let me write first informally and then say how this can be formalized. Suppose we just write formulas. So if it is adjoint, then we have a natural transformation. F composed F star to the identity. It will be identity of C, if I'm correct. It's a co-unit of the adjunction and would be F star would be identity of B goes to F star composed with F. It would be the unit of adjunction. So, and suppose they're given on the level of complexes, then as functors. So we can take the cone of this and make this into a functor. And we can take a cone of this one and make this into an endofunctor. This would be from C to C, and this would be from B to B. Now the functor is called spherical if those are equivalences. Spherical functors means equivalence. I simplify a little. In fact, in this theory, there are various criteria how to prove that, knowing that one is equivalence and a little more, how to prove that the other is equivalence. But anyway, so here is the concept. And if you look at this, that the cone is categorification of the difference, and this matches very nicely this concept. So let me give an example of what a spherical functor is, or example of a situation. Suppose we have the derived category of vector spaces over a field K. Again, I really mean DG enhancement, so the category of complexes. So how we can construct a functor to the category C? Well, it's generated by the field itself, and this should be sent to some object. The object is called spherical. If its endomorphism algebra looks like homology of the sphere. Equals, say, K. Let me write xj equals K if j equals 0 and some number n, so-called n spherical, and 0 otherwise. So in this case, one can see like one of the cones is a self-equivalence. We do the cone, we kill, to the identity, we kill the x0, and what remains is xn. So again, I simplify just a little. There is an extra condition that this k and the second k are interchanged by the Serre functor. But let me not go there. So this implies, so then the functor spherical, functor f. So such functors appear for like the structure sheaf of a Calabi-Yau variety, orientation sheaf of constant sheaf on an oriented topological manifold, and so on. So already this gives us some topological idea. So suppose that now let me return to the next sort of simplest at the same time kind of eternal geometric case of surfaces and graphs on surfaces. So on, let's say, stratified Riemann surfaces. So we have something. So what do we have? We have a surface X and a set of possible singular points. A is a finite subset. It will be something like this. We'll have a surface, and then a few points. Surface possibly with boundary, and some points in which perverse sheaves are allowed to have a singularity. So then naively, I want to introduce a concept of perverse schober, which would mean a categorified perverse sheaf. So So schober belongs to the line of agricultural terminology. It basically means something like a sheaf, but in German. So it's a different word. So given this example, it almost explains everything that we want from such a structure. So if you take neighborhood at every point, well, it's this situation. So and we know what it is. If you're outside those points, it's a local system. It's a sheaf. And the sheaf can be easily formalized. So naively, local system of category on x minus a, and a spherical functor near every x in A, somehow glued together. So I want to spend the rest of the talk on making the structure more precise in different ways, and showing relations with other concepts and constructions. Okay. Let me just discuss. So what I will do, I will discuss some elementary aspects of perverse sheaves, but sometimes which are not so well known, and then see what are their categorical analogs. Let me call this part localization on a skeleton. And again, I will stick to the case of 2 dimensions. So let me notice the following elementary proposition. Suppose F is a constructible sheaf on a surface. Then is perverse, and perverse I mean as here with respect to the middle perversity, because we want duality on self-duality of the category. So is perverse. So for whatever set of singularity it has, if and only if, for every graph, k inside x. Well, if you have a graph, we can write sheaves of hypercohomology with support in this graph. And this is 0 for j not equal to 0. In other words, if I denote this embedding by I, that in the sheaf theoretic notation, I factorial of f will be identified with H0, with support in K of f, is a single sheaf. So if you ask in what sense perverse sheaves are better, well, in this sense, they're better. So it produces a single sheaf. So let me call it, I don't know, R K of f. Then we have a functor from the category of perverse sheaves to the category of sheaves on K. We have the functor RK from perv of x to sheaves on K. And this is because only single homology, it's an exact functor of a billion categories. And in fact, so all such the descriptions by Quivers are mostly based on this type of purity. It's a purity statement. We start from perverse sheaf and get a single sheaf. So this, why this got us excited, because this concept matches what's known the proposal in symplectic geometry introduced by Kontsevich called localization of Fukaya category. So localization of Fukaya category on Lagrangian skeleton. So in this situation, it should give a sheaf of Lagrangian skeleton, I denoted by K, supposedly gives a sheaf of categories on K. So perverse sheaves, they do something similar. In a way, they know about this idea. And so that's why we wanted their categorification so that it can be useful in this type of study. Now let me take up this idea a little bit. As you see, it's extremely elementary. let me explain the connection with this type of descriptions. So what would be somehow a simple example of this? Suppose X is a disk. Suppose we have this thing, and in the center we may have a singularity. And suppose K is this. So suppose K is diameter. Then we have a single sheaf on this interval, and R, its stock at 0 would be the space of vanishing cycles, and the stock at any other point, say at 1, F1 would be the space of nearby cycles. And the map from here to here, for instance, in the description is simply the sheaf structure. However, it doesn't have to be like this. In fact, already this property should be more or less enough to prove the only if part of this proposition. But let's consider a more general case. Suppose this n plus 1 valent vertex. Then what we get are K of F, and this is the point 0. It would be, well, it's a base change of this situation by the n plus 1 sheeted covering. So it would be space of vanishing cycles, but with respect to the function Zn plus 1. And it can be identified in terms of original phi and psi. So this would be isomorphic, but not canonical, to psi to the n plus phi. So to choose an isomorphism, we need to choose which of those spokes is number 1. We need to break the cyclic order to a total order. So it means that on this space, there is an action of nth root of monodromy, n plus 1. So what we want to do is to understand the analog of such constructions in the spherical functor case and how to glue them together. So we want the categorical analog. So that it would be not a sheaf of vector spaces, but a sheaf of categories. So let me, how much time I have? Oh, okay. Let me discuss a little more the issue of the symmetry. So we can identify it, but if we choose a different beginning, we'll identify it in a different way. So there is cyclic symmetry acting on such thing. Let me try to understand the cyclic symmetry. So in fact, it's not cyclic symmetry, because if we do n plus 1 times, we don't get the identity, we get the monodromy. So let me call this paracyclic symmetry. And then its categorification will appear as Waldhausen S construction, which was, of course, mentioned here as a fundamental concept of K-theory. So let's look at the situation. Suppose we start with an arrow. Psi from B from psi to phi. So any linear operator. So how can we view this type of construction for every n? Well, we can make it out of this linear map. We can consider it as a two-term complex and form the corresponding Picard category. Psi. So it corresponds, it's very familiar in theory of algebraic stacks. So its objects is, set of objects is phi, set of morphism is psi cross phi. The two arrows here, one projection and the other then the action, so it's more. So if you take now the nerve of this Picard category, so the next thing in the nerve is in the nerve we have objects, morphisms, pairs of morphisms, and so on. What we get exactly a collection of those things. So we have nerve psi to phi. It's a simplicial vector space. If you write that nerve part n would be precisely psi to the n plus phi. They are arranged into simplicial structure. So now, let me recall that the simplicial category used in simplicial objects is embedded into a cyclic category of Alan-Kohn and its versions. So here we have standard objects, del I, Si. Yeah, those objects correspond to intervals. Yeah, so that's embedded into Kohn category lambda. So in this category, this ordinal will be rotated in a circle. So there will be a little more faces. It will be one more degeneracy, and inside n will be an operator tau n. So rotation and tau n to the n plus 1 equals 1. This is a cyclic category of Kohn used in cyclic homology. And it has a version, it has, if you wish, universal cover called the paracyclic category. So paracyclic. This is cyclic, in which this circle is replaced by a spiral, if you wish. So some sort of universal cover. Yeah. So in here we have tau n. So, but no requirement. So just isomorphism. So, and if you put tau, the collection of tau n to the n plus 1, it's a central family. So natural transformation from the identity functor to itself. Now I want to say the following proposition. Again, it's an elementary fact, but it sort of gives a slightly different point of view on the construction. Proposition. That suppose you want to extend a simplicial structure to a paracyclic structure. Then doing this is equivalent of writing a map in the other direction so that we get a perverse sheaf. So extending simplicial structure on nerve of psi to phi. Suppose this map is B, is the same, is equivalent in one-to-one correspondence. So maps A from phi to psi such that 1 minus AB and 1 minus BA are invertible. This actually can be recovered, can be dug out as a very particular case in some paper of Dwyer-Kahn about Dold-Kahn correspondence for cyclic objects. However, of course, the relation with perverse sheaves, you need to be aware of them to understand this. So in other words, the category of perverse sheaves on a disk is identified with the category of paracyclic vector spaces which, as simplicial vector spaces, are nerves of something. And nerve of something, then it would be a Picard category, and so on, which as simplicial ones are nerves of something. And of course, this is the famous Siegel condition. So how to say when a category simplicial set is a nerve? It's a Siegel condition. So now let me discuss a categorical analog of this. And I'll keep this board there. called categorification, or let's say category phi is 2, Waldhausen S construction. So let me explain what it is. So suppose B is a triangulated category, but with an enhancement. So it's either DG or as a stable infinity cat Perluria. So which means that we have in one of the formulations, it means that we have Home spaces are enriched in the category of simplicial sets or in topological spaces. Then there is a version of the Waldhausen construction. In this case, it's more classical in the case when B is an exact category or an abelian category, but it can be performed in this context. And it's a categorical version of the space K pi 1. So let me write it like this. S dot of B is approximately K B1. And it's using K theory. So simplicial, in this case, it will be a simplicial DG category. Or in some DG category. Which means for every n, there will be an Sn. So Sn of B. So naively, it is diagrams of objects Bij for 0 less or equal than I, less than j, less or equal than n, plus arrows. And arrows correspond to the functors. So it's a diagram from the category of morphisms of this ordinal n to B, such that for every I less than j less than k, we have a distinguished triangle, Bij, the corresponding map, Bjk, is exact. Now, what is it precisely means by being exact? If we're dealing in terms of, if it using the formalism stable infinity categories, it means that this square is Cartesian and co-Cartesian. If we work in the DG setting, then we embed this into a slightly bigger category, again, a sort of more universal thing called En, and have a DG functor. So in this En, there will be those triangles will be encoded. So, and let me do it here. So such, as in the classical case, the projection of S and B to the category of arrows like this, B01, B02, B0n, would be an equivalence or appropriate quasi-equivalence. I just write this thing. So the size of this is approximately B to the n. And more precisely, it's not B to the n, but it has a semi-orthogonal decomposition of several copies of B. So it will be a filtration of triangulated subcategories, and the quotient by previous one, so in this, would be identified with B. So this is the absolute situation, which is the analog of classifying space of a group. Now we can also write the analog of classifying space of a two-term complex. Maybe I'll do it here. Now suppose f from B to C is a DG functor. Now, in this case, there is a relative version of Waldhausen S construction, which is already in, which is one of the papers of Waldhausen. So it's defined as the fiber product, very naive fiber product. We have SNB goes to SNC, and here we go to the Sn plus 1 of C. This is induced by F, and this is del n plus 1. It is defined as a fiber product. So its size approximately b to the n cross C. So and if you look, it's really a categorification, can be seen as a categorification of the nerve of this groupoid. And has also semi-orthogonal decomposition with several copies of B and one copy of C. Now I want to formulate a statement that which is a statement is a categorical analog of that proposition. So it's a theorem that S of B can be made into a paracyclic object if and only if F is spherical. So in one direction, it's a construction of the paracyclic structure. Again, I'm saying that there will be a certain replacement, and the paracyclic category would act on certain replacement. And on the other hand, even in the other direction, it's interesting, and it says that. Oh, yes, I'm sorry, yes. S of F, yeah, S of F. Yes. Yes, F is spherical. So in the other case, a certain question of periodicity of the semi-orthogonal decomposition, which in simpler cases has been studied before, and it will be enough for us. So in particular, while we have only C and no B, then we simply have S of C. Yes. I don't know. So if we have only B and C is trivial, then we have S dot of B. It is paracyclic. It means that there is a rotation of exact triangles. There is action of paracyclic category. So up to homotopy, a rotation of exact triangle would be again an exact triangle. A sort of a version of this together with the spherical twists, the automorphisms given by spherical functors. So now, how much time I have? Oh, I still have time. Excellent. So using this as a local, so this is a local model for this type of category, for this type of sheaf. Local model. Those things give local model for RK, for sheaf of categories of a spherical functor. A schober associated to a spherical functor, to F. So this is, if you view F as a datum of categorified perverse sheaf, then those things would appear as geometric traces, as geometric sheaves of categories, stocks of geometric sheaves of categories corresponding to graphs on a surface. In fact, one can do a little more and describe, sort of give a definition of schobers, not unlike the definition of sheaves. But for this, we need a definition of perverse sheaves, not unlike the definition of sheaves. And this is, of course, a classical problem in the category, in the theory of perverse sheaves. But for surfaces, it can be done rather naturally. So let me call it like this: perverse schobers as data on what we call Milnor pairs. Let me explain. So first of all, let me give definition of this. So we start with a stratified surface, just a surface and a bunch of points. Then a Milnor pair is a pair of two open sets, U inside U prime, open, so inside X, such that U is a disk, U prime is this disjoint union of disks. And now let me make a picture. So those disks are embedded only, so to say, at the boundary. So this is U, and this is U prime. So next condition is that U minus U prime is contractible. That means that they lie sort of at the boundary and also contain at most one critical point. So contain at most one element of A. So the reason for the name Milnor pair, it looks like the area when f, real part of f of z, greater than epsilon. So U prime, when you have a homomorphic function, it looks like something like this. Or it can be thought of as a thickening of a graph. Yeah, we have four of them, yeah. So it's a kind of thickening of the graph. So again, we have an easy observation. Suppose now F is a perverse sheaf. Then for such a pair, we only have the zero hypercohomology of relative hypercohomology with coefficient in F. And so we are left with the data of vector spaces called E of U prime will be H0. So as such, we get a bunch of purely abelian data associated to a perverse sheaf. And it is a pleasant exercise to just define perverse sheaves like this. So we have, this thing gives a functor from the appropriate partial ordered set of Milnor pairs. There's a poset, the opposite, and we get a functor from this to vector space, some kind of presheaf, E. One can characterize those presheaves. So it's purely abelian data. So. Now, I must say that this description is close to what Macpherson, in some of his notes, is called Faree sheaves. So there's notes of Macpherson on the internet. Except here, it's purely abelian. In this case, there still can be in different degrees. Here, it's purely abelian set of data. So proposition that perv XA as a morphic category of E satisfying some obvious axioms, such as, for instance, homotopy invariance, and should be homotopy invariance relative to this set of points. So homotopy. Let me call it number one. I will have two normalization. So if you have something like this, so if it is U and this is U prime, and there is no A, then in this case, there is no point from A, then E of u prime equals 0. And number 3 is exactness, which is consequence of homological sequence of a triple whenever we can write a triple so that all the 3 things would satisfy this condition. So, and that would be like this. That would be, let me try to make a picture of this. So we have u and u prime, something like this. And now imagine let's do, suppose this will be V. This will be V. Then we will have 3 Milnor pairs. So whenever we have a situation we can write 3 of them, would be something like this. E of u V, then would be E of V u prime intersected with V. And here would be E of u prime united with V. So if you have any sheaf and any 3 things, that would be a long exact sequence. But in this case, it should be exact. Now, I should also say that this set that doesn't form a Grothendieck topology. So that is not, because the intersections of such cannot be easily covered. So we don't have a good concept of descent. However, this description is simple enough so that we can do the categorical analog. We should just say that to every such pair we associate a category with certain properties. What is this? Okay. So, and that will be a definition, a perverse schober on XA is, well, the datum should involve all enhancement. This would be an infinity functor called S from mil up to stable infinity categories, satisfying similar axioms. So let me, to shorten, let me write 1 as is, 2 as is, 3 should be replaced by Riemann, replaced by semi-orthogonal decomposition. By now, in Riemann, there are also 2 functors in the other way. Yeah. And in fact, in those other adjoint functors, it's required that they be given by certain data here. So adjoint functors prescribed with adjoints. So not that they exist, but they're given by something. Adjoints prescribed. And there is one more property here for the next level. It's a partial descent for something like this. Let me make a picture. Suppose I have my disk like this, and it's supposed to separate it into 2 parts. So for each, like this. So, and this would correspond to a graph which we want to cut along the edge. So, and we have one open set like this and another open set like this. And that would be U1 and U2. So then we'll have something, a datum like U prime, U1 intersected U prime, U2 intersected U prime, and U12 U12 intersect with U prime. So in this U12 will have only two disks. So it will be descent for this diagram. So the corresponding diagram of S would be a pullback. So now the statement, let me formulate our results about this. So this is first for C0, this is the same as a spherical functor. Number two, that every graph K and X, for every graph, such a datum S, so such S, gives a sheaf of categories, again, would be of infinity categories, stable infinity categories, R K of S on K. Now, the interesting case is when the graph spans the surface. So 3, if K spans X, and X is a surface which should definitely have a boundary and can even have corners, so possibly corners. So I maybe draw something like this. So a surface with corners and maybe a hole, and then a spanning graph would come with each leg into a corner. And everything else, the surface would be contractible to the graph. So I won't go into discussion of spanning. Then, so there's a sheaf of categories. We can take the naive concept of global sections. I write gamma of K, R K of S. So what does it mean? It simply means homotopy limit. So then this is canonically, coherently independent on the choice of K, is coherently independent. And that's what we want to call the topological Fukaya category with coefficients in S, F of XS. So that's a categorified analog of cohomology, of some particular cohomology. So topological. So if we do this for a perverse sheaf, then what we'll get, it's rather clear what we get, and it would be the decategorification of this. It would be simply, how should I write? It was simply like this: zeroth Kuiper homology of X, well, del X minus corners, well, say S. So that's somehow the meaning of this. So it will change if we introduce corners, so this concept will change. Okay, so now I have just a few minutes. Maybe I should say, like, really briefly, how this gives a categorified analog of Picard-Lefschetz theory. I will be. Categorified Picard-Lefschetz. Now, usual perverse sheaves are provide formalism for Picard-Lefschetz theory, so to say, without Lefschetz pencils. So suppose we have a perverse sheaf just on the plane with some set of singularities. Let's say some set of points, say W1, Wn. Then suppose we have two such points, say Wi and Wj. Then near here we have a disk. Near here we have a disk. So suppose we have a path gamma going from Wi to Wj without meeting any other points. Then, so here we have a disk. So phi and psi are really local systems on this disk. So that would be, here would be phi I. It will be mapped into psi I. By transition will go to psi j, and will get to phi j. We have a map, phi I, psi j, phi j. Let's call it mij of gamma. So now, what happens when gamma moves in such a way that it crosses another point? So it would be this situation. It would be, say, the phi I here, phi j here, would be phi k here. We'll have this path, say this is alpha, this is beta, this is gamma. But now suppose we want to move this gamma. So there is nothing here, but we write this one, would be gamma prime. And then we'll have a Picard-Lefschetz formula, would be like this. Mik of gamma prime equals Mik of gamma plus Mjk of beta, M composed Mij of alpha. This is just a version of 1 minus AB in the definition of, in the local definition of perverse sheaves. But this is really the classical Picard-Lefschetz formula and will appear as such. So classical Picard-Lefschetz will appear for perverse sheaf F associated to a Lefschetz pencil. So now in the category phi setting, we have not the formula with addition, but we have exact triangle. So for a schober in this definition, we have phi I are categories for S from Ci. So phi I categories, Mij gamma functors. And when we do something like this, we'll get Picard-Lefschetz exact triangles. What time is it? Okay, I need to turn. So let me say a few brief words about the so-called algebra of the infrared. By Gayotto Murvita. So it was introduced to explain some categorical aspects of behavior of physical theories. And the typical situation is when we have a Lefschetz pencil on holomorphic Morse function, and inside we have the set A as a critical values. So we look at convex geometry of the set A. We look at convex hull of the set A. And so what they introduced was some Lie infinity algebra acting by deformations on an A-infinity algebra, and in particular, deformation elements. So what I want to say, and this is a work with Soebelman, that this can be generalized to the setting. This can be done for a setting when we have a schober. So joint recent with Soebelman in progress. So for every schober S, we have a similar formalism. In particular, by deformation, we get by deformation for the categorified homology of the disks with coefficient in S, where disk is considered with one corner, so one corner. So we have disk which contains all the critical points. So in this case, the collection of Picard-Lefschetz triangle provides deformation data, provides a Maurer-Cartan element in the L-infinity algebra, which deforms the A-infinity algebra to algebra describing this category. So it means that this structure, a perverse schober, seems relevant to this type of study of behavior of physical theories in the limit. So and that's also I find it very interesting. Thank you very much.